learning module 3. So in this learning module, we're going to study the fluid flow and heat transfer in a 3D mixing elbow. The problem to be considered in this learning module is shown schematically in the following figure, as you see. A cold fluid at 293.15 Kelvin flows into the pipe through a large inlet. We have the inlet conditions here, and it mixes with a warmer fluid which enters through this small little pipe, and the temperature of the flow which is entering is also given at 313.15 degrees Kelvin. It enters through a smaller inlet located at the elbow. This configuration, the mixing elbow configuration, is encountered in many applications like piping systems, power plants, process industries, and many other applications. So it is often important to predict the flow field and temperature field in the area of the mixing. So we want to know how these two flows will mix together and what is the expected temperature or the temperature distribution in this. Uh, excuse me, in this configuration. So because the geometry of a mixing elbow is symmetric, uh, we can model only half of the mixing elbow. So instead of a full scale model, we work on the half of it, but we will have to learn how to deal with symmetry boundary conditions. So today, you're going to learn how to use turbulence models, symmetry boundary condition, and we'll try to understand post-processing multiple simulations in CFD post. Okay, so on the schematic that you see, we have the temperature in both inlets. We also know the velocity of the flow entering normal to the inlets in the larger inlet and in the smaller inlet, and we know all the geometry parameters, all the dimensions, and of course all the properties of this elbow. Since this is not really a modeling course, a CAD course, we will not spend time on developing geometry. We're going to assume you either know how to make a 3D geometry in a software like SolidWorks or ANSYS Design Modeler. If this is not the case for you, there will be tutorials attached to this video which helps you and guide you through creating the geometry. For the purpose of this video, we're going to assume that the model is already generated and we are trying to model the flow and temperature conditions. Okay, let's proceed with this simulation. So I'm gonna open the ANSYS workbench. So I already have one open here. I'm going to drag fluid flow fluent and drop it in the project schematic area. So one option that I have, for example, if I've created the geometry in another software, or it's been given to me, I can import the geometry instead of actually double clicking here and going to the design modeler. So in order to do that, what I can do, I can right click on the geometry and then go to import geometry. I can browse and find the geometry that I have. So I already have the file of the elbow geometry. So I'm going to open that. Once I do it, the the 3D model is implemented in the software. So like, for example, I could double click on the geometry and take a look inside of the design modeler. Here's, as you see, the geometry is created. I can um, look at it. I have two inputs and out, so this would be my large input, this is my small input or inlet, and this is my the outlet from this elbow. So the details here of how to create this geometry, as I said, are in the tutorial that is attached. But for the purpose of this video, we're going to assume this is already created. And as you see, we only modeled half of this geometry because it wouldn't make sense to do a full geometry if both flow and temperature are symmetric, which is the case in our model. So let's go ahead and close this. We import the geometry to the design modeler. As you see, this check mark will appear here, which says there is a geometry there. We can, as you saw, we can double click on the geometry and check different parameters there. But the next step in any CFD simulation is to generate a right mesh. So I'm gonna double click on the mesh generator here. The meshing software will open and shows me the geometry. So the geometry has now been transferred to the mesh generator. If I click on generate mesh without doing anything, it's going to generate a very uncontrolled and not very good mesh. So you can still use it, but your results will not be accurate. So we will learn how to control a 3D geometry mesh for a 3D geometry here. But in order to start, let's start with assigning some names here. So I'm going to assign some name selections, calling different surfaces names that the software understands. For example, I'm going to click on this face selector, click on this surface. When I do that, these two planes appear here, which is telling me, okay, by clicking at this point, you have two choices. You can select two surfaces. One is the one that is highlighted here. The other one is in fact on the other side, because the software cannot really distinguish between the two, but I know that this is the one that I really want to work with. So with that selected, I will right click here, go to create named selection, and I'm gonna call this velocity inlet large, because it's my larger velocity inlet. Then I click OK. Then on the project tree, a named selection has been created. If I click on this, it's going to show me that I have called this surface velocity inlet. So the ANSYS software is smart in a way that the names that you choose here, actually they have meanings. For example, now Fluent software in the next step will know that this is an inlet boundary, and most likely you want to introduce a velocity value for that. Okay, now before moving to next step, I have to assign different names. So for example, I would like to select this small surface here by clicking on it, right clicking, go to create name selection, and I call this velocity inlet small. Now I have assigned two inlet surfaces. Now I would like to rotate the model, zoom in here, and select my outlet, which is this surface. Again, right click here, create name selection, and I'm gonna call this pressure outlet. This way the solver will know this is a pressure boundary. The other surface, which is something we need to assign, is this surface. This is actually the symmetry surface. So I'm going to right click here, go to create name selection, and call this symmetry, and click OK. So I do not really need to assign any other surfaces, because by default it will be converted to the surfaces that I do not assign a name will be considered as walls. So now how can we control the mesh? That's our next step. In order to do that, we have to work with this bottom area of the surface, the left corner of the ANSYS window, which is details of mesh. I can, by default, my solver understands that this is a CFD simulation. I'm going to use Fluent, but I can go click on sizing and change the relevance center from coarse to fine. If I now create a new mesh, generate mesh, as you can see, a more finer mesh has been created, which is still not as good as I want, but it is in fact finer than the previous mesh. I need to have more control over how fine I want to create a mesh. So next step, I can, in order to have a control over sizing, I will be selecting the whole geometry by selecting this body, right click here, go to insert, and then sizing. If I do that, then I have control over the size of the elements that that will be generated. I can go down here to the details, see there is a line for element size. By default is 8 times 10 to the minus 3. I think this is very large. I want to have a smaller element. 6 times 10 to the minus 3 is a good value here. There is not there is no real wrong or right values. The right values will be figured out by doing the computations and evaluating the results. That's why CFD is not just simply plugging some values into equation. It needs some experience that you gain as you progress. Okay, now again I can create mesh, and you will see the mesh is now really fine, but still it's not giving me an important characteristics. So if I zoom in here, you'll see that near the surfaces, near the walls, the elements that are generated are still pretty large. This is not something I like, because I know there are a lot of gradients, a lot of variations of different parameters like velocity, temperature, and all that near these walls. So I would like to have more control there. So in order to do this, I'm gonna go first to the mesh and open the quality menu here and change the smoothing from medium to high. This way the transition between the surface elements will be higher, meaning that you will not have a large node near a small node, which is not something you really like for computations. So next step is to create that layer attached to the walls, which we call the inflation layer. I open the inflation menu here, and I change the automatic inflation from none to program controlled. By default, the software creates 5 layers of inflation, and the growth rate is 1.2, which is okay for our for current geometry. So I just click on generate mesh again. It takes a while to create the mesh, and then now if I look at the mesh, I can see that inflation layer next to the wall. I could control the amount of the layers of inflation. So as you see, there are 1, 2, 3, 4, 5 layers. I could increase this to 10 or smaller values, and I have control over the growth rate. So each node here is 1.2 times the previous node. But this is a good geometry for what I want to do with this model, so I'm gonna just keep that. What I can do at this point, I would like to save my project. So I will just click on update. This way the mesh will be sent to Fluent, and I can see in the message that the mesh translation to Fluent was successful. This is a good sign. I can simply close the meshing. Okay, Now I'm ready to configure the software. Before doing that, I would like to save this project. I know where I want to have this saved, so I just copy the address, paste it here, and I call this elbow dash 2 as my project name. Takes a minute to save. Then if you are curious to know what kind of files are being generated, you can always go to view and go to files and kind of monitor the files that this software is generating as we progress. So far we have a few files like the mesh file, and you know where it is now saved at. We have the geometry file, the mesh database, the workbench file. There are a bunch of different types of files that are being created as we do progress in the modeling. So for example, in order to locate these files, I can go to the folders that are usually generated next to my model and proceed to find the files here. You don't really need to do this, but just in case you want to know what kind of files are being generated, this is how to do it. Okay, now we're ready to, in fact, proceed with the solver. So what I'm gonna do, I'm going to click on setup. The Fluent launcher will tell me you're ready to start. Click on double precision. I want to have a faster computation. I do parallel processing with 8 processors because I know my computer has 8 processors there. Then I simply click on OK. So when I do this, the Fluent now shows me the model that is sent from the mesher, and I can like zoom in, take a look at different parts, and yeah, it's just ready for computation. So there are certain things that you want to do after you import the mesh file to the solver. So first thing is always clicking on check. Check will make sure you don't have any negative volume nodes. In more complicated geometry, this may happen, and your mesh generation may fail, and you'll see that the mesh has failed. But in this case, it's not. I can also click on report quality. Report quality is showing me some statistics about the quality of the mesh. So the quality of the mesh plays a very significant role in the accuracy and stability of my computation. So you always want to make sure you click on the report quality and monitor this parameter, minimum orthogonal quality. So the minimum cell or orthogonality is an important indicator of mesh quality. So values for orthogonality can vary between 0 and 1, with lower values indicating a poor quality mesh, and larger values are essentially better. So in general, you want to avoid minimum orthogonal quality less than 0.01. Those mesh qualities are gonna usually give you very bad results. If this is very small, then to improve the orthogonal quality, you can use inverse orthogonal quality in Fluent meshing, which we will discuss later on. Also, this is a maximum aspect ratio of the cell, which is 31. So there is one cell somewhere here, which one of its dimensions is 31 times the other dimension, which is okay at this point. Usually you also want to keep this not very large. So very skewed mesh elements can also cause a problem for your computation. So before moving forward, I also want to make sure the units that I'm gonna use are correct. So I go to length and create on millimeters because this geometry is created in millimeters. If your geometry is created in meters, you don't have to do this step. Now we're ready to set up the physical model. We start with setting up the physical model here. It's going to be a pressure-based simulation with absolute velocity formulation, and it's a steady state, so we keep that as is. We do not really need to turn on gravity because we're not modeling natural convection, and gravity is not going to really play a major role here. Again, you need to gain the experience to know when you need to turn on the gravity and when it is not really necessary to do so. Um, okay, but what we need to do is clicking here on models and turn on the energy equation. I can click on energy because we're going to solve heat transfer and flow field, and click on energy equation, click OK. The energy equation will be now solved. And since I know that the flow inside the pipe is actually turbulent, I click on viscous and select K epsilon model. There are a bunch of different turbulence models that may or may not be a good choice for your specific equation, but K epsilon is a standard method for modeling turbulence, so we go with that. You do not really need to change any of the constants parameters that you see on the right side on this menu. These are from empirical correlations that is coming from the literature, so we can keep those as is unless you're doing research on turbulence modeling. Then the wall treatment, near wall treatment, always make sure you click on enhance wall treatment. This way your results will be more valid closer to surfaces. So with that, we can click on OK. The rest of these models are not something we want to solve in this case. So we can proceed to materials. So we have to include the material property. So I click on fluid, and I need to introduce a new material. So one way is to go to Fluent database and search for water, but I don't want to do it. I don't want to actually implement my own. So I change the name from air to water. It's a fluid. Density, I want to change it to 1000 kilograms per meter cubed. The heat specific heat is in fact 4216 for water. Thermal conductivity value I'm going to use is 0.677. And finally, the viscosity of water is 8 times 10 to the minus 4 kilogram per meter second. So I added all the properties. I click on generate slash create. The software is going to ask me whether I would like to overwrite air or I would like to generate a new material. I do not want to overwrite air, so I click no. Therefore, a new material called water is generated for me. So I can safely close this window and proceed to the next step. In the next step, I have to tell the software that my fluid, which is, the area that I'm going to solve the equation, is in fact water. By default, it's going to be air. If you click on fluid, you'll see that the material name is selected as air. But I'm going to change this to water and click on OK. There's nothing else needs to be changed, so just click on OK. So by doing this, now the software knows that the material that is inside this elbow is water with the specifications that we provided. Okay, now next step is to defining my boundary conditions. The boundary conditions are a little bit tricky here. I have two inlets, one outlet, and a symmetry. I can click on the velocity inlet large in the first step. The software will open this window for me in which I can change certain parameters specific to the inlet, to the larger inlet here. I can define velocity parameters, like I can give the software magnitude and I tell it that it's normal to the boundary, or if I want I can give components, XYZ components, which is not very usual. Usually you do magnitude normal to the boundary, and the value of velocity that I have is actually zero point 0.4 meters per second. Another parameter that you need to change is down here. So since we're dealing with a turbulence model, we have to tell the software what is the situation at the inlet. So turbulent intensity, you can always leave it at 5. That's a good number by default. But instead of dealing with turbulence viscosity ratio, I would like to work with hydraulic diameter. So by definition, hydraulic diameter is 4 times area, the cross-section area over the wetted perimeter. We know that from fluid mechanics class. So if you solve this for this case, it will be 100 millimeter for the larger inlet. So now I can click on OK. I have to exactly, oh, I forgot to assign something important. So if I click on thermal, then I can tell the software what is the temperature that is going inside my solution domain from the larger inlet, and that value is 293.15. Remember that you have to convert degree C to degree Kelvin here. Now that I do this, I'm ready to click OK. With this small uh, surface, with the small inlet, I go through the same steps. So the velocity magnitude as given on the problem statement, you can take a quick look here and see the small is 1.2 meters per second actually. So I change this from 0 to 1.2 meters per second. Leave the turbulence intensity, but I give the hydraulic diameter. The hydraulic diameter is going to be different this time because it's a smaller tube at the inlet of a smaller inlet. So you have to find the hydraulic diameter again for this tiny little surface. Now, thermal conditions. So what is the temperature of the flow coming in? Again, going to the problem statement, it's 40 degrees C. Converting that to degree Kelvin, it's 313.15. Then I'm ready to click OK. For pressure outlet, usually there is nothing to change. So we can just assume and accept whatever is here because we don't expect the flow to come back from that surface, so we simply keep it as is. Sometimes you want to change the temperature of the backflow if the flow is sucked back to the surface to the solution domain, but we know it's not going to happen in this case. So just click on OK for now. Now, so the rest of the boundaries are not really something we need to worry about. For example, the wall is a no slip condition, and thermal condition is zero heat flux, which is just telling us that this is an insulated elbow. So nothing to change here. The symmetry also is just symmetry. Software knows how to deal with the symmetry boundary condition by default. Nothing to change here. Alternatively, I could select on all these values. They're just the same. Different manuals doing the same thing. Okay, now let's move on to solution control. I click on methods. So pressure velocity coupling, simple algorithm, we can leave it as is. the gradients for this type of problems in which you deal with um, turbulence and uh, tetrahedral meshes, you can select a green Gauss node based. This gives you better results. Nothing here needs to be changed unless you want to, work with a second order for turbulent equations, but nothing really you need to change here. Then we can also select control. These are under relaxation factors, controlling the convergence. You don't need to change that. Let's go to monitor or monitor residuals. Since this is a 3D geometry, if I increase this convergence criteria less than the default, my computations is going to take much more time. So I'm gonna leave it as is. If you would like to have more accurate results, you can always increase these values to smaller numbers, to 10 to the minus 6, for example. But for now, I just leave it as is. Okay, now we're ready to start the computation. Before doing so, I should initialize. This time I click on initialize and click on and make sure the hybrid initialization is selected. Click on initialize. It just assigns some values for the initial guess, and it does it based on an algorithm that it's implemented within software. Now, actually, we're ready to start the computation. So in order to do that, I click on Run Calculation and change the number of iteration to a very large value. Usually you don't really get to that. Your solution converges before reaching that many number of iterations. So then we click on Calculate, and we sit back and look at the behavior of the code. We expect these residuals to uh, drop as the software is solving the governing equations in an iterative way. So it's usually going to take anywhere between a couple of 10 or a couple of hundred, a couple of thousand iterations sometimes, depending on your quality of mesh, your complications of your geometry, complications of the equations you're solving. So the number of iteration is not really under your control. Sometimes, if you don't do a good job of meshing, your solution will not converge, or if your results or your model does not represent a physical phenomena, your computations will not converge. So, but usually when you have this behavior, computation is going into the right direction, and finally it tells you that the calculation is complete and your solution is now converged. Okay, now some results is generated, and there are different ways to look at it. So for example, I can click on graphics here and make a contour plot of, let's say, temperature on the symmetry surface with a field option. Click on this, and as you can see, now I have created a contour plot on that symmetry line. As expected, I have high velocities coming here, low velocity here, and they merge together. I'm sorry, high temperature, low temperature, they mix, and at the outlet you may have larger values of temperature. You can do the same thing with velocity, for example. Again, we're looking at the velocity magnitude, and this area has a larger velocity because it was given a larger input here in the small inlet. Okay, so this is one way of looking at your results, but this time we want to do a little bit more in CFD post. So at this point, we just save the project. It's gonna tell us, give us a warning. Usually just click on OK. It will save this, the project and the results, and you can simply close Fluent. So now in my project schematic, I have all the check marks except for results. I can look at open CFD post and see how my results looking. So CFD post has more options and give me more opportunity to look at the results in a more interesting way. So here's CFD post. There are a lot of things I can do here. For example, I can generate, as before, a contour plot of, let's say, temperature distribution. Where do I want to have this contour plot? I can do it on different surfaces here, but I select the symmetry surface, and I can control the number of colors that are gonna be used. I just select 50, and by clicking apply, the contour plot is generated. And as you see, for example, I can click here, a more high quality contour plot is generated for you. Other things you can do, for example, you can create a 3D contour plot. So let's turn off this for a second. I can click on the volume rendering option, click OK, then ask the software to generate a 3D rendering of temperature, and click on apply. Then it takes a while usually, and you can see that a 3D contour plot of velocity is created, temperature is created. Or you can change this to pressure and look at the 3D contour plot of pressure all over my solution domain. You can do this for velocity as well by selecting velocity magnitude. Of course, we expect higher velocities here, and you can investigate the results and make sure it makes physical sense. Uh, Other ways of looking at the results, let's turn off this for a second. I can have streamlines, and the streamlines, I want it to be in all the domains, and you can select where you want these streamlines to start. So since we have two inlets, I can select both of them by clicking on this icon and push the control button, click velocity inlet large, velocity inlet small, click on OK. How many points do I want? I can increase that. This is the points in which the streamlines are going to be initiated. So let's select, let's say 80, and click on apply. So by doing so, you can see that the software generates the streamlines of the flow. This is in fact the path that the particles of water is going to go through, and the colors are velocity of the flow at each point. You could also generate a 3D vector plot by clicking on vector. The location should be on your interior, so the fluid essentially, and we can click on apply, and this way a 3D vector plot is generated. It's usually good to zoom in and see how the flow is behaving. Sometimes you may see things that you can tell they're not right. For example, if in this case, if I see that the flow is reversed in this direction, I know this is not right. I know it doesn't make physical sense. Or if I see that the flow is going back to my inlet, for example, for any reason, that I can be sure that something is not right. Okay, now we have looked at different ways of looking at the results here. Now, on the next step, I would like to first save this project, and we want to do a little bit of a parametric analysis, parametric design. Let's say I would like to see the effect of a larger inlet here. What happens if I increase this this inlet, the small inlet. What if I increase its diameter? What would the results look like in that case? So in order to do that, I have two different options. I can either redo everything here, which is going to be, you know, overriding your previous results, or you can be smart and right click here and click on duplicate. By duplicating your computations, a new flow, a new chain of ANSYS software modules will be created right on the right side. And I'm gonna call this, I change the name to a larger inlet. Okay, now I have to modify the geometry, of course, so I click on the geometry generation. So I want to increase this diameter. In order to do that, I can click on cylinder 1, and go down here to the radius, which is now 12.5. I change this from 12.5 millimeter to 19 millimeters and create generate. So as you saw, the diameter of this inlet has now increased. Now I will close the design modeler. Now I have to update the mesh because my geometry has changed. So click on mesh and click on yes because the geometry has changed now. There is nothing to change in the mesh generator except for I have to make sure a new mesh is generated. So I click on generate mesh. I will keep everything as before. So click on mesh and you'll see that a mesh is generated for a larger inlet here. Nothing else needs to be changed. So I can close meshing. You could simply click on this icon. Okay, so it seems like we need an update. So we right click here and we click update. Update will make sure everything is right with the mesh and sends the mesh to my solver. Okay, now I'm ready to redo this computation for the larger inlet. So I click on setup. It's gonna tell me the mesh is changed, but I'm fine with that. Click on OK. The only thing that needs to be changed in the updated version of my simulation is the boundary condition at the small inlet, because I have already changed the diameter and that will affect the hydraulic diameter of this boundary. So I have to modify this again. 4 times cross section over the wetted area for this case is 38. I don't change anything else. I click on OK, and again I right go to initialize, click on initialize in hybrid way, then go to run calculation and click on calculate. So now this time I have to wait a little bit more, but in general, as you see, my residuals are being reduced, and this is a good sign. So I simply wait until the solution is converged. If you see that your residuals are increasing, that's usually not a good sign. In some cases, it may take hours or days for a solution to converge. But as long as you see a declining trend in the residuals, that's always good. Otherwise, you probably need to change, modify your model. Okay, my second computation is also converged, so calculation complete. I click on OK. I go to close Fluent. And I have two solutions now. This is a larger inlet. This is my original model. And look at the number of files that are now generated by the software, because I now have two different sets of models and they have their own corresponding files. So one way of looking at this results is to again clicking on the CFD post for the larger inlet situation, but I kind of want to do both. I want to look at both results under same software. So the one way of doing this is going to component systems and drag a result window and drop it right here. Now I need to import my results from both of these computation to this design. So I click on solution here, keep pushing the left click and drop it right here. A line will be formed that is telling me, okay, your solution from the first computation is now sent to the result. I do the same thing. So I click on solution, I keep clicking and drop it right on this result. Again, result from the second is now sent to the CFD post, this result section now. So now if I click on results, my software is going to show me both of the computation results at the same time. And this is sometimes very helpful, especially when you're changing parameters and you want to know its effect on flow, temperature, or any other parameter. It's usually a good thing to do. So for example, again, I can do a contour plot of temperature on the symmetry line with 20 colors. Click on apply and it shows me the the results corresponding to both larger inlet and a smaller inlet. And this is what we expect to see. There will be more velocity coming, more mass coming here, more velocity, and your hot fluid is now extended to larger areas inside the knee. And as you can guess, even qualitatively, you can see that the temperature at the exit should be larger compared to the case with a smaller inlet. You can do the same thing for all other cases. Again, I can generate a 3D plot of, let's say, velocity magnitude. Rendering may take some time, especially if your model is large, but you can have a better understanding of how the flow looks like in both cases. They're not very different in this case, but if you do apply other changes, you can investigate that here as well.